Boom. Hey, welcome to the Coffee Compiler Club. Here today to talk about compilers and language runtimes and anything and everything to do with language implementations. Everyone's recorded. We're going to be on YouTube in a few hours. Assuming I get YouTube sorted out. It took me a week to get the last one posted because YouTube just silently would fail on everything I attempted to do, including installing, uninstalling, browsers, rebooting, blah, blah, blah. I had to switch to Bing to do the upload. And then it just went like, oh, normal, just natural. Of course it uploads just fine. I was like, what the hell? Like how did Bing get involved that it did this thing?
Were
And
you uploading on Firefox?
yeah, I was uploading with Firefox. And the other comments I got was, oh, you should attempt this with Chrome. Of course, I didn't have Chrome installed because Chrome gave me issues back in the day, and I hate Chrome at the moment. So fine. So I could get over my hate of Chrome and be fine. Hey, Thalia, is that how you pronounce your name?
Hey, it's Talia, by the way,
Thalia, tall
but
T,
anything's good.
tall
Yeah.
T, tall T. Okay, fine. Yeah, okay. So we had a big go around this morning on Sea of Nodes, and I know you're in the wrong time zone. You want to ask a question before you bow out?
I don't have any specific questions at the moment. I think you answered. Well, actually, I did have a question about the start node.
Yeah.
It's kind of jumping a bit to future chapters, but I was under the assumption that I would have a start node per function when functions are introduced.
Um, Probably we will, well, we'll do something along those lines. Yes, it'll be something like a start. We might have a function header instead of a start node.
Uh-huh.
And then a separate start. It's like depends whether you want to have one compilation unit include multiple functions or every function its own compilation unit. Yeah. So a compilation unit has something like a start, but if we're going to have multiple functions in a compilation unit, probably because we're going to do like inlining and things like that, then we'll have function headers as well.
Uh-huh.
So there may be another layer added in there to separate functions from start. I think that's probably because simple is not a runtime, so it's not a JET, so it's all ahead of time compilation. So probably makes sense. Multiple functions in a compilation unit. So now you need a start, and then and the start's really just a gathering point. It's just a way to make the graph algorithms easier. So you just run for all outputs, for all inputs in all directions, and you get everybody.
Okay.
Okay. So the other thing I wanted to say here on YouTube is because the optimistic and pessimistic things run all throughout the simple Sea of Nodes implementation. I think probably people who are like formal compiler theory are all good with it, and people who don't have that always ask questions and always get confused about what's going on there. So I was just going to rant on it for a few minutes and then go back to like having a conversation. So this is a case where there's some high theory that the implementation you can 99% ignore. And the high theory gives you these wonderful properties that don't show up obviously, and then suddenly shit works because high theory. The actual implementations like Peepholes that say things like add of x plus 0 is x. That Peephole just does a little local observation, makes a little local change. It's all very simple. No one cares. It's all obvious what you're doing there. The constant propagation thing has this optimistic versus pessimistic and monotonicity properties that are easy to implement, easy to follow, and not obvious. And because of them, you get this optimistic versus pessimistic algorithm choices. So that deserves more commentary. So when you start out with people and we're doing, in simple, we're doing parsing of the IR and we're doing peepholes while doing the IR, we always have this funny game where the parser has yet to see what is to come and you're busy optimizing behind its back. And how much optimization can you do when you have no idea what is coming up in the future? So it's pessimistic in that you're going to make optimizations that are valid no matter what the parser sees in the future. Okay, it seems kind of straightforward and actually turns out to be really easy to do. But this limits the set of optimizations you can do to things that are always correct. So this is what I call the pessimistic side of things. You start with a correct program. It has something you parsed and some unknown mystery yet to be parsed. And it can do anything in that yet to be parsed. So you can treat it like, hey, it's a part of the program that does the worst possible things it could ever do. Reads everything, writes everything, updates everything, does horrible things, all it can do. Because you don't know what it's going to do. But the stuff you've read, you know exactly what it is. And now you can do pessimistic things with it. Pessimistic, always correct transformations. So these are things like global value numbering, two things, two inputs, they're the same op, same inputs, they must compute the same value, done. Add of x plus 0, subtract of x minus x is 0, things like that. These are all pessimistic. You make a transformation, update the graph that's been parsed, and the future doesn't care, doesn't know, doesn't care what you're going to do. It's all great. In those pessimistic transforms, there's a set of different ones that have different kind of views or different kind of behaviors. And there's the compute call, which is where the confusion comes from. And then there's idealize. Turns out there's also dead code elimination, replacing constants with constant nodes, constant computations with constant nodes. And let's say dead code, constants, global value numbering. So these are all things that do a Peephole transformation based on local facts that are locally correct, that are pessimistically always correct. Compute is where it gets weird. Compute says, I'm going to tell you something about the type of a node. And if I can tell you the type is a constant, then I can do this Peephole transform, replace you with a constant and get rid of the computation. Great. But in general, I tell you something about the type of a node. And in the pessimistic world, all the types start basically at the bottommost type, most conservative type. And you learn things about the program as you parse. And in that learning, you begin to lift the types. So I have some variable x, I don't know anything about it, I give it a bottom. Oh, it's declared int type, well, I lift it to int bottom. I assign it to a 17, well, I lift it again from int bottom to 17. So it keeps lifting over time. This is always pessimistically correct, and it's always safe to do, and it's great, and it gives you some set of optimizations. But it leaves on the table the set of optimistic optimizations, and these can't be done in an idealized call. The optimistic ones, this is actually, I'm just using the word optimistic as counterpoint to pessimistic. The classical algorithm I'm using here is sparse conditional constant propagation, where the constants in the constant propagation are anything and everything in the type lattice. So it can be constants like 17 or pi, but it can be constants like something as a pointer that is null or not null. Or in the case of Java, you can be capital I integer or capital number or capital whatever the different class hierarchies and subchilds and subclasses and superclasses. The ints can be in ranges. The ranges can be small ints or big ints or whatever. So you can have all kinds of things in the type lattice. These are all constants. They're just types. So the optimistic algorithm does a thing that the pessimistic one can't. He says, I'm going to hope for the best. This is my hopes and dreams comment, Yarden, and then find out what reality is. So I'm going to start everyone at top, and notice the parser starts everyone at bottom and lifts. The sparse conditional constant propagation is going to start everyone at top and fall. So everyone's set to the best possible solution they can be. They are things like top is basically, you can think of it as it's all possible constants, all at the same time. It's completely illegal. It can't be 17 and 3 and pi all at once. But that's the conceptual notion. It's everything you ever want it to be. It's magical and it's illegal. So then you go ask the compute call, hey, is this correct? And the compute call looks at his inputs at some point and says, you assigned a 17 here. It's not top. It can't be. It's 17. And so you begin to fall in the lattice. And as you fall, you go visit your neighbors and you have to go fall them as well because their inputs are top, they're 17 or whatever, and things gradually fall down as opposed to lift up from the pessimistic side. When it stabilizes, you monotonically have a better answer. It might be the same. It's generally a little bit better. Sometimes it's a lot better. Sometimes you can discover constants that kill code. You can kill off whole swaths of program code. This actually happens a lot in the land of Java, where because of lazy class loading, somewhere along the line, somebody reads a config file. The config file says, use this display variant option versus the aqua random blue theme versus whatever. And suddenly all the other themes die and become dead and go away. So you get these things a lot at big constants that decide state of the world things. And then they show up in small cases all over the map. So, okay, fine. How does that actually work, that start high and fall down? Well, it's the same thing as the start low and lift if you just look at the types because of high theory. And the theory here is that you're monotonic and your transfer functions are monotonic. What's a transfer function? Well, that's a compute call. The compute calls are monotonic in the lattice. The lattice has these properties that it's symmetric and complete and bounded and ranked and blah, blah, blah. And the amount of code involved and the amount of what happens to code is really small. It's very sort of simple and obvious. But because of high theory, you're guaranteed that the work list will fall. It will fall to a fixed point. So it'll terminate linear time. And that the answer is better than the pessimistic side. So that's the pessimistic versus optimistic. There is an algorithm that will give you a better answer. It's linear time. And it's fast. It's cheap linear. And most major compilers have this optimization pass in them. This is a very common compiler hack.
I have a question. I get a sense of it, but it will be good for the when you say fall, they always fall within a type. So when you discover it's int, it stays in that lane, if you will, and starts to fall. So it cannot be int and string at the same time. That would be a type error. So
right. So I'm starting from a place of I am looking at a well-known sound program. So I'm trying to optimize one. There's another version I'm doing in AA and a little bit in simple where I'm using the same process to do actual typing. So this all works even if you have illegal or broken or bad types. As long as your lattice has those lattice properties, monotonicity I'm talking about, your transfer functions are monotonic. And in fact, I am doing this in simple in a little ways. So here in simple, the null pointer checks. I have a nullable type. Simple cannot throw a null pointer exception. You'll get a compiler error beforehand. How does he know when you have a compiler error? When is a pointer null or not? Well, he does. It's like Kotlin. You declared things nullable or not, and then he proves that all your places are nullable or not. And if you're missing a null check, he'll tell you, okay, great. So where does he complain? Well, he complains everywhere where the type system, after the best possible optimization pass, can't prove that you have a not null value when you're about to do a pointer deref. Okay, what is the level of proof involved? Well, right now we just have a pessimistic pass and simple. With an optimistic pass, we'll get a better proof. And some places which would have been compiler errors for a null pointer throw will go away. And the compiler will, the simple will prove you don't need a check. If you wrote one, they'll just elit it as dead code.
Yeah, but when you say fall, so if you fall, let's say in the integer lane, because I don't have a
so let's do the
it,
string fall.
Cannot. I have a question about it. Cannot fall to nothing. It will always be integer because you can't have a runtime representation of nothing at least.
This is not true. So this is the high theory part coming in.
Okay.
So if the goal here is I'm going to do typing in simple. And I can now improve my typing in a number of ways. One of them is I can claim dead code has no type errors. And I totally have a representation for something that is both an int and a string at the same time. I call it bottom. I can't execute it. I can't write code for it, but I have it in the type lattice. It's just the lattice has a top and like ints and string lanes, and then bottom. And bottom is bottom for memory, it's for control, and for this, and for all kinds of crap. You can't do anything with bottom. Bottom's an error case. Okay, if I get a bottom in the program during one of these transformation optimization passes, whatever, I have an error that's lurking or pending or something. If along the way I prove that code is dead and it gets thrown on the floor and disappears, I no longer have a bottom in the program. So if you write some junk ass code that says x equals 17 here, if random x is 17, else x equals quote ABC. So completely broken code, can't do it. What's the type of x? I don't know. Okay, and then it turns out that that's guarded by an if false after optimization proves it's false. The code goes dead, gets thrown away. I don't care. It's got a bottom type. Fine.
So how can you prove the code is a dead code without having the large part of the program? So you cannot. Will it be code, or it's within a function? Let's say within some scope that you know that you cannot.
You're going to look at the IR. You're going to type every node. If the type of the node turns into false, and then an if consumes it, right? So an if node says, "What's the type of my predicate?" Oh, my predicate's false, or it's true. It
Okay,
could be random, I don't know. And then both arms are true, but maybe it's just one of the two. Okay, the other path is dead. That's a Peephole transformation that throws code away.
Okay, that I will let that pass because you figure out what is a branch, so you can optimize it away. Okay.
Yeah. This is the conditional part of sparse conditional constant propagation. If the condition is true or false, then the code executes. If the condition is not going to, if the conditions of the code never executes, it doesn't produce any interesting values in the lattice theory sense, that they're not consumed. And that lets you get stronger types. And this is actually a really common occurrence for around null pointer checks. I wrote some of those I'll write one in the damn, I'll take some of these examples and put them in the doc for people.
Sorry, I've gotta go.
Hey, yeah. Well, nice seeing you.
Yeah, hope I can join next week too.
Yeah.
Bye-bye.
Great. All right. Bye-bye. Okay. So let's go. Let me go find. So I'm sharing this. I'm going to go ahead and example and throw it in.
By the way, I had a quick question. You mentioned high theory a bunch of times. What is that?
Well, it's just theory for people who haven't had any formal theory. There's nothing.
Okay.
It's just me being snarky about comments about academics.
All right.
It's the shit I learned in grad school that I know is taught in grad school even to this day. But if you've not got a compiler background or taken grad courses in compilers, you may not have seen it. And that burned a couple people like Dibiendu, who bowed out for a while ago, didn't have that theory and got confused by the lack of it by quite a bit. And it took a bunch of times to try and help them sort out what it meant and why. And I think it's not really hard stuff, but if you've never seen it before, well, okay, it's a mystery. So here's an example that's not conditional, that's a little weird, but it's really simple. I'm going to highlight it there. Okay, what's the value of X? Well, you and I can look at that and say it's always 1. But if you go ask the sort of the Peephole only version of the world here, and I go a little SSA naming. So this is what you get out of SSA form. And of course, simple is always running around SSA form here. I guess this would be 2. Okay, when the Peephole starts, comes out of the parser says X is 1. I come to this phi here, X0 is 1. I come to this phi. Can I highlight you? No, well, that's really bad. So what's the value of X1? Well, it's the phi of X0, which is a 1, and the back edge. What's the back edge value? I don't know, because the parser hasn't seen the code that follows. So the back edge is assumed to be the worst possible thing, bottom. Okay, so that means the phi is bottom. Okay, then he comes down here to this expression, 2 minus bottom. Well, that's bottom. And then he comes back around and he says, oh, the phi takes a bottom on the back edge. It got a bottom on the back edge and hit a fixed point. I'm stable. The answer is X is bottom. I don't know anything about it. Or maybe it's integer bottom, right? Because I can say 2 minus is a subtract node, gives me an integer, but it's nothing special. The optimistic version says everyone starts at top. So I walk through X0. It's set at top. It's assigned to 1. It falls to a 1. Fine. I come to the phi. I say merge X0 and X2. Well, what's X2? It's top because everything got initialized to the top. And X0 is a 1. 1 and meat of top is 1. I don't fall very far. I fall to 1. Okay, now I do 2 minus 1. Well, I get a 1. Well, now it's 1 around the back edge. It had been at top. Now it's a back. Now it's a 1. Now it's a phi merging 1 and 1. Okay. The answer is a 1. So the optimistic version finds the constant 1, where the pessimistic one does not. So this one's a little weird because it's kind of a dorky one. Here's a somewhat more realistic version where if I assume pointer is not null, then I never execute statement 1. Pointer remains not null, and statement 1 goes dead. But if I start in the parser doing pessimistic bottom-up things, When I get to the phi at the head of the loop, pointer might be null around the back edge. I don't know. And because it might be null, I have to assume S1 will execute. And here I'm gonna go make it more obvious here. And now it's definitely going to be null. And then, you know, S1's valid and I have to emit code for it. I have to do the test and emit code for S1. But as soon as I do an optimistic version, it's never null. And I can delete it to get an optimization there. So that's sort of the difference between optimistic and pessimistic. The top-down approach can find things strictly more often than the bottom-up version. They can tie, but otherwise it'll win. For that to work,
But there's nothing that stops you from having a bounding range where you're doing optimistic and pessimistic simultaneously and just carrying around a tuple.
there is, because I don't know what the future unknown parse thing is. So the optimistic version says, I don't know what comes next. And I have to assume bottom.
Right. I'm just saying, as you walk the node graph, you can keep at each point both a optimistic and pessimistic.
No.
Here's what I know.
Yeah, again, no, in a useful way. Yes, technically, again, no, in a useful way. So what happens here is that pessimistically, I can also do graph transformations, like rewriting graph chunks, which the optimistic version can't do if he thinks he has a constant, but he's not sure yet. The optimistic version has to hit a fixed point. So I wrote this code this way, and you can get the fact that pointer's null. But suppose the actual code was this, and I start optimistically at the top of the loop saying, hey, pointer's not null, go to the else clause. Oh, now pointer might be null, and it has to fall again. So when is it legal to kill pointer equal nulls? Well, in the optimistic pass, it's only legal when you stabilize and hit a fixed point. The pessimistic version is always correct if you can prove it, but the pessimistic version can't ever prove pointer is null, and the optimistic version can't use the fact that he has a null until he hits a fixed point. Meanwhile, I was trying to find a fixed point. If the pessimistic version also does a graph rewrite, the optimistic version is screwed up and has to start over from scratch. Does that make sense?
It does make sense, but it is still a little surprising to me that you can't use the pessimistic guy to eliminate nodes and do things and make the problem smaller as you go and do a bunch of peepholes.
You do. That's the whole point of the pessimistic guide, but you don't do it while you're running the optimistic, or you can't use the optimistic results until you hit a
can't use them yet, but you can make it cheaper to find the fixed points because you're eliminating pieces of the graph as you find them.
So here's the trick with that. The optimistic version is really fast in linear time. It's already the same cost.
You think you're better off finishing the pessimistic version than running the optimistic
and then
version
running the optimistic one, yeah. Because if you make a change in the pessimistic side, because you know something, the optimistic side will have already taken the worst result because the idealized transformations are outside the domain of the type system. So the idealized transformations can improve the situation for the types without the type system being able to recognize the ambiguity of this could be this good if idealized cleans me up. And if it doesn't ever clean me up, then I am only this good, right? So I get these two different versions, except there's many idealized calls, so I get many different versions and they all exponentially interact. So I can't tell on the optimistic side. So as soon as a pessimistic does a peephole that rewrites the graph and improves the situation, the optimistic version has already lost his optimism in a way he cannot recover without a restart. So the easy answer is you run pessimistic to a fixed point, finish the parse, get it cleaned out. That's all linear time as well. Now run another linear pass. That's actually, it's cheap linear and find your optimistic. Now you have some new type info. You rerun the pessimistic stuff, which is actually incrementally, it's incremental. It's not just linear, it's incremental. So whatever constants you find, only that needs to be touched by the pessimistic side, who then promptly replaces the constant calculations.
How cached are the results of these analyses? Do you store the pessimistic and optimistic results on each node?
I restore them in the same field on every node. This is classic array of struct of array representation question.
Right.
The pessimistic version touches it all the time, so I put it in the node. Back in the day in C2, I fooled with having a side array of types indexed by node ID. Basically, I have an array of types for the type calculations and an array of nodes, an array of this. It's struct of arrays. Turns out that kind of inconvenient and didn't really help because you wanted the types all the time. So I just went to the array of structs instead, array of nodes.
So with pessimistic being invalidated by changes made during optimistic, it seems like this array approach would be advantageous though, because then you can just clear the whole thing at once.
Okay, so I don't know, you said something that maybe you meant the right thing, but I heard it funny. When you're done with the pessimistic and it's stable and you've gotten what you can get out of it, the best you can do a pessimistic. Now you want to try the optimistic. You need to reset everyone to top. That's a touch all nodes, set everyone to top. And that's, constant time more efficient in an array because you just do a linear array fill to top as a pointer constant. That's really quick. On the other hand, the graph walk to touch all the top fields is actually still also pretty quick. And in the grand scheme of compiler optimization things, you're going to spend way more time on register allocation. So,
Okay.
you're right. There is an optimization here.
I
There's an
mean,
optimization question.
you could play games like the optimistic ones are using positive numbers and the pessimistic ones are using negative numbers. Now when you switch, if you ever find a number with the wrong side, oh, that was from the last run.
Oh, you go
Just stop.
revisit people. I played these one-off games. There's a lot of graph walks going on. Graph walks have cycles and sharing, so you need a visit bit. So why not have one visit bit, and then when you're done with a walk, you come back around and flip the expected direction of the visit bit and visit again. That only works if you visit all nodes. As soon as you're only visiting some subset, then the visit bits get randomized and you can't use them that way. So I gave it up on the visit bits. They're kept in a side array called a bit set, and it's just a classical bit set, but it's an array of bits that's indexed by the node name. So it is in a side array. Yeah, okay. Was that everything we touched out of this morning's Discord? I think we also touched x minus x equals 0 is a compute call and not an idealized call, because and what is the rule? The rule is if you're going to produce a new type for a node, you're going to produce a constant because you're going to replace it with a constant, but actually you produce a new type. That type is a constant, so you're going to expect a constant replacement. But if you get a type for a node that's better than what you otherwise have, you put it in a compute call. Whereas idealize generally doesn't mess with types on a node. Instead, it replaces nodes with other nodes. They may have new types. They may improve or allow you to compute new types. But the first step for idealize, or the first way to think about them, is they rewrite the graph. They change the shape of the graph. Compute calls do not change the shape of the graph. They change the types of a node. And I guess another way to think about it is idealize does something with relationships between nodes, and compute says something about a node.
So how are they called differently? I understand the differences in their results, but are they called at different points?
Yeah, because they can do different things. Let me figure out the sharing here. We're going to pull up. We'll pull up Emacs here. And that probably means I have to go dork with my size here. Font has its own issues. Okay, oh, and it's way oversized to the right. Oh, I didn't share yet. Okay, hang on. There we go. Share. Okay, so let's go look at. Here's a compute call for subtract. Where is it going to get called? And here's an idealize. Doesn't do anything.
We are still not seeing.
Oh, I'm still not sharing. What?
Yep.
Hit the share button. How about now?
Yeah.
Okay.
Can you make a little bit bigger? Oh,
is it big enough or do you need bigger?
a little bit bigger.
A little bit bigger.
a little bit.
Yeah. How about now?
Excellent.
Okay. See if I can get my, hang on. Oh, Emacs won't give me the, yeah, it's too old for Zoom. There it goes. Okay, fine. I get my bottom status line back. So compute's doing something here where it's telling me a new type if your inputs are the same, or if your inputs are all constants, I'm going to give you the constant computation. Otherwise, I don't know what I get. Fine. Where's it called? It's called in two places here. Let's see. We're going to go the big one. Well, not the big one. The obvious one is Peephole. Peephole opt. Here's Peephole opt. So Peephole opt gets called every time from Peephole, which gets called every time in the parser. So ignoring the debug turnout, which I could probably get rid of these days, you call Peephole, and then if you come back with something that says you're dead, you get dead coded. But if you come back with an interesting result, you just Peephole again until you get no progress, where null is no progress, and I'm done. So what is Peephole doing? He calls compute first up. Why is this calling set type from compute? So compute is functional. It has no side effects. That's a grand purpose goal because it's going to be used in the bottom up and top down versions. And also we want to assert that you're monotonic because people write transfer functions, write compute calls all the time. You edit and hack and you add improvements, like we just today added subtract of x minus x is 0. You blow monotonicity on them all the time by mistake. You want to assert on it. Fine. So then you want to go to set type here, which all it's going to do is say, get the old type. And if you're identical, which is very common, just do nothing. Otherwise, set it. But meanwhile, there's an assert. Type is a old. And the nulls only happen if you're talking about a first time brand new node who hasn't has a compute call ever called before. So if you blow that assert, you blew your monotonicity on your compute call, go fix your compute call. Back up to here. So here's compute. That comes up first. Now, if I get a constant out of that, I'll replace you with a constant. This is an idealizing like graph rewrite call. It's common across all nodes. So it doesn't happen in all nodes. Ideal calls happens once here, shared for all nodes. Global value numbering, also known as common subexpression elimination. Same thing, everybody does it. So I don't have it in every node individually. I have one common shared place. Do a hash table get. If I miss, I put. If I hit, I got a prior version, and I go ahead and kill one of you and return the other guy, return the new dude I got out of you. So in, this is what's getting tested. In is in the hash table. I got a hit, I'm returning in and deleting self. Then the idealized call happens. So this is the pessimistic version of things as done incrementally node by node by node in the parser. There's another incremental version that's the official looping algorithm. This is the work list. While work.pop is not empty, go get a node. If it's not dead, call people, just the same people we had all along. And you get to compute and idealize and everything else. If you got to change, there's some more work to get your neighbors found because neighbors get complicated in general. And the parser version of neighbors has all these future unknown parse things that are going to be neighbors someday, but aren't here yet. Whereas this version has all the neighbors known, so he has to actually go visit all the neighbors. He also has this giant progress assert, which is in squared, we ignore it, but that's it. So pessimistically, compute is and idealize are called in Peephole opt, and they're called either once when a node first appears in the parser, so every parser makes a node, calls Peephole on it, or they're in this work list where you just spin the work list till it runs dry. The optimistic code I don't have, but it would have the same approach. It would say, visit all nodes, set the top, put them on the work list. While work list not empty, pull it, do a compute. If you get progress, put your neighbors on the work list and repeat until the work list runs dry. Then at the end, you go visit everybody who made progress and see that you can do something with them. You visit everybody again and say, hey, if you're a constant now, but not a constant node, go get on the work list, go make progress. So does that answer where these things are called?
Yeah, it does. Thank you.
Okay. And that might have been what
About the
happened.
work list. So for arithmetic operations, it seems like you could just do them bottom up once when they're first parsed. But you get into trouble with that approach once you throw phi's into the mix.
Exactly.
Okay.
That's exactly this guy, where I say X is 1, wow, rand, right? X equals 2 minus X, because there's a phi involved.
Yeah, sure.
You're in trouble. Yeah, because you have a loop. Because there's a cycle where a constant appears, and this is a very simple cycle, but I could have arbitrary random code here. So very big cycle, but it's a cycle. The
Right.
pessimistic version can never eat the whole cycle, or his horizon of view is always finitely sized, and some cycles always bigger than any peephole. So you can't swallow the whole cycle in a peephole and say, oh, I recognize this entire thing as a single giant peephole, I'll just rewrite it. Whereas the optimistic version, in fact, does the whole cycle all at once. And
and when you were talking about this example earlier, you said X received the type of integer bottom.
yeah,
Was that on the condition that your subtraction is wrapping instead of, because then it would say nothing about the value?
the decision, so there's a couple decisions you can go here on how to deal with this. I'm doing, Deviendo talked me into doing the versions a little bit more aggressive. The C2 actually doesn't do this, but it's totally legal. I know that a result of an integer subtract is always an integer. I'm not doing overflows. I'm doing wrapping 2's complement sine 2's complement wrapping integer math. Therefore, any int minus any int is always an int. In fact, I'll tell you anything minus an int, subtract, integer subtract always returns me an integer. I don't care what my inputs are. I'm going to get an integer out. This means that the parser can even lift a value of bottom to int, right? So here, if I go x0 is a 1, and here's my x1 is 0 and 2. Okay, so the parser here is like, what is x2? Well, he doesn't know. So he's going to say, I want to go to the whole type bottom. So type bottom, the worst case. I have no idea. Somebody wrote pointer math, floats and ints. What, I don't care. It's bottom. I have no idea. Here he's going to say, wait a second, right? What is int2, subtract of type at bottom? So he asked this question by calling the compute call, and the answer is always at least int bottom, right? It's at least int bottom. Or it's a program error, but int bottom's correct here because I have to do it's monotonic. As long as I've hit my high theory goals, it's monotonicity. As long as I hit monotonic, I can choose int bottom. And if it turns out that the back edge is something horrific like string ABC, I'll get a type error. And then I'm not going to compile this program anyhow. But the type theory doesn't care. He'll compute a valid integer type and life will go on.
That's really interesting to me that you don't resolve types before dealing in the IR. That's just an assumption that I've had about IRs.
Right. It's not that I don't resolve them. I am not harmed by processing illegal code. The type system is correct, semantically correct, as it processes illegal code. All
Sure.
illegal code types perfectly well in the lattice. Then
I'd
before I
imagine,
emit code, yeah.
I'd imagine with say you have type class for subtraction, I'd imagine with the more complex types there where your implementation of the type class can specify a different result type of the subtraction would make it seems like you'd probably want to resolve instances before you lower to the IR so you can have that information first.
Yeah, so now you're talking, I have, as a program semantics, I allow subtract to be some sort of overloaded operator. The overloaded operator has different semantics according to its inputs. If I'm Python, I do the runtime check every time. Hey, are you trying to add 2 strings? Oh, that's okay. I'll add strings. I'll concat strings. Are you trying to add 2 floats? That's okay. You trying to add int and float? Well, I'll widen the int to a float. So he's doing a runtime check every time. If I'm doing static compilation, strong static typing, same question can arise, but at compile time, hey, you're adding int and float. You probably mean to widen that int to a float. That's okay. Hey, you're adding string and string. Oh, I can do that. That's okay. But he has to know statically what those types are in order to specialize. But that's not really the type system's issue. That's really what you want to do with your program semantics. And what do you mean when you say add 2 things? You know, I'm doing x plus y. What's that mean? Well, what's x? What's y? Well, okay, I can come up with a bunch of combinations that works well on, combinations for what that's should be an error. When do I report that and when do I specialize on it? So that gets into, you know, language design. It's the type system, though, has no care here. He can gleefully represent it all.
So suppose you're compiling a statically typed language. It seems to me that type checking on its own would be a simpler algorithm to implement than interleaving it with your other optimizations. Has that been your experience as well?
So I came from this different domain. So I had simple types back in the day, and it was all obvious, and I knew them all ahead of time. I came to Java to do this fast compiler thing, and the Java bytecodes have their types handed to you ahead of time. So I already had the correct set of things. I go to AA as an experiment because I observe that I can mostly regenerate shit like generics from C2's type analysis. Like I can unwind the type erasure mostly. So can I do it all the way? And the answer was that I needed some more stuff, but I could do it all the way. Now, is it more or less simpler? One of the things that comes out of that is I get a stronger type system in the sense that I can type more programs. I can type programs that your normal type analysis says are illegal and cannot be typed. And I can say, yes, I can type this program. It has a strong semantic meaning. I all know what it is. It's all fine. And that's shit like, you know, what we just talked about earlier with this kind of thing here. Right, somewhere over here, I said I got some x or bar x, or what is x? So I'm doing type inferencing. What do I do for x here? Okay, if I throw this at I want to say an ML like language, a Haskell like language, he's going to say, well, you can't do that. That's not good. If I throw it at what I'm doing in simple and in AA, I'll say, oh, this code is dead, so it doesn't count. So, oh, x is 99. It's easy.
Interesting. So I guess you get occurrence typing for free, essentially.
Yes, I am computing a reasonable, a good typing for as part of normal optimization. I'm computing a typing as well. Now that I have a typing already, I don't need another typing. I'm going to use the typing I got out of my optimizer. So at the end of the optimization pass, I look for type errors, and that's in simple right now. After the idealize call, after the iteration finishes, the peoples are done, he says, oh, look for errors. And there's a couple nodes that'll compute an error. And that's the biggest one of those is the loads and stores check the pointer for known to be not null.
Does this also compile if false is a call to a function that is very big? Maybe not.
I'm sorry, say that again?
What if instead of false, like in the predicate of the if, what if that is instead a function call?
Yeah, right.
Like to a function that can be constant evaluated, like
right.
Would that also compile?
Yeah, if the optimizer can reduce that to false, it will pass the type check. So the type analysis always runs. So he doesn't care about illegal code. He gives you a type. So if E0 himself is a function call that inlines, and the function call itself now has to inline. You know, I have to compute a value for it. However, that's done. I don't actually have to inline to get that type out. I mean, I have to get some result out here. So function is something that does blah, blah, blah. Right. I mean, this. So if I run type analysis on this, again, I can do this optimistically as a whole program unit. So somebody asked about starts or not starts, right? So there's a start node. Well, then there's something for main as a function header for main as a node, right? And again, here's a function header, function, and, you know, blah, right? Okay, something like that. So I have a bigger, complicated program, has more nodes, but I compute it all at once. As part of the computation, this thing gets typed. Type to return false, and then that will just flow in right here. And this means, you know, so the typing will fold that at optimistic, actually pessimistic in this case, anything, it'll fold that, and then boom, it'll be done. So
isn't that kind of brittle? Like, because then you could like for instance, let's say you're editing some function and then you make it just as big to cross over the inlining threshold, and suddenly you can get type errors somewhere at some random call site because like, isn't that very frustrating experience?
Okay, so I haven't written this code enough in anger to know if it's frustrating or not. Here you blatantly wrote broken code. This is just stupid. Okay, it must be false. Okay, why did you write broken code that you're hoping will disappear? Well, I can come up with an easy answer here. Right, and you know, else if Linux, blah, blah, blah. And here is like, you know, some sys.read call, which has args and Windows specific. And of course, this code will die if you compile it on a Mac, and this code will die if you know, compile it on a Windows. Except if these are known constants, it won't. So I can imagine writing this code. Now, is this frustrating if is Windows doesn't inline? Well, it has to produce a constant at the optimistic version. It doesn't have to inline.
You
can just inline threshold.
You can just raise the constant. So if the function FCN can be figured out that it's all constants and can be optimized to be that all its arguments are constants, it will be optimized. It will be reduced to a constant value, and that will work.
I mean, the constant evaluator also has limits, right? Like it's not gonna like run forever.
So the problem here would become that it's not that it cannot reduce it, but if you fall silently to reduce it, here it will be here in the one case it has to unify the both arms or some of the arms, and the other case, if you figure out that FCN is a constant, it will produce a different type. So you have to be careful. Is that what you expect? So, at least to me, I understand it that way.
I think this is basically where I'm at with this. So this is an experiment for me that I haven't run to the end. I'm kind of running it a small way and simple, where I'm allowing null pointer checks to be removed by the optimistic version of things. So if the pessimistic version can't prove not a null, you have an unobvious null property. And you could say that that's good enough. I need to have that. You just put a null check in and deal, even though the user knows it can never fail. He needs to have a null check written in the code that says, if null, panic, something like that. The compiler can't prove it's not going to happen. So what's the compiler going to do? What's the code going to do when it runs? And he thinks it's going to happen. Well, if you know it can't, you just put panic in and tell the compiler, ignore this. It's a cast that you're ignoring the result or whatever. Okay, so this is simple doing it with nulls. And as soon as I go to the optimistic version, I'll get more of those checks. Those compiler can't prove it becomes compiler can prove it, and that's okay. Now get in here in this example, same kind of story. I don't really need inlining on Windows, is OS X. I need that it constant propagates to a false or a true.
Yeah, that can include FCN calls different function that can be constant for that OA. So it has to trace. So, but we don't have a keyword, let's say a const, that it has to be compiler assure that will be reduced to a constant value.
Right,
So it can,
right. Here, I'll get you an error on the wrong OS if you didn't fold the constant. So down here, I'm going to hear, oh, return false, return true. But instead, of course, you're obviously going to do return config check, right? And whatever config check does. Well, somebody looks up in some OS spec somewhere and comes back, includes a, in C, you'll include a pound header file. And
so in this instance, the is Windows config checked will have to be probed that can it return a constant, the function itself. So
all
can
three of them need to return a constant. And now how can I prove that? And they return different constants according to whatever config you're at here. I don't know, whatever.
But here I sense the error reporting has to be much more precise. I have to tell you that it cannot produce this type, but this because this value is not constant. So because
I wouldn't claim that. Maybe, but that would require really me wanting or really putting in some sort of keyword in that says I'm expecting a constant, give me an error if it's not. That was exactly the keyword you're just talking about a second ago.
Yes.
Okay. And if you don't have that, instead what'll happen is you'll get some error here. We say like, error, illegal, whatever, sys.read for, mac.sys.read or whatever. You'll get some sort of, hey, I'm like here. And if you look at the code, it'll be like, if Windows error, what the hell? Why did is Windows return me true on my Mac? Well, then you have to go figure out why the OS pound include header file didn't fold up constantly. I don't know. All these things are obnoxious in different ways. In the actual land of C, a lot of these things are done with pound if defs.
Yes.
Which are just as obnoxious.
They cannot be tracked in the for type.
Yeah, right. If the pound if def failed, you'll get the same bug. Now, same error message. Okay, somebody fixes this. It's a high priority bug. You fix it. Okay, life goes on. Now, if I'm writing miles and miles of junk application, not low-level Windows system-y code, and I get these errors out, what do you want to do about it? It's like I did an obvious one. Okay, people fix their OSs. Fine.
Yeah.
Now I got a giant junky piece of code, and somewhere in the world it says, if I'm on a Spring Boot version of blah, 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 and or this or that, run my hibernation technology this way, else Kubernetes launch, blah, blah, blah. What the fuck? It goes on forever.
Yeah.
I don't know. Seems like a reasonable thing to me. It gives me a strictly stronger typing. Everything that I would have otherwise.
Yes. We have discussed it many times or in the CC. The potential here is that it can introduce a code that will become outdated because if you only test for is Windows, this part will be only tested, but that would allow the other branch to become outdated. And if some time ago the code will go to a different machine that is macOS, and surprise, the code hasn't been updated in ages. And
but the same thing is true in existing systems as well.
I doesn't. It's the same problem in different form. So it's the same problem. Yes.
Yeah, it's the same problem, different form. Yeah, that's fair enough.
Okay, so Advance is curious because he has a similar concept in his programming language. So it's interesting.
I mean, do I understand correctly? I mean, maybe I completely misunderstood, but like, would that also mean that, let's say a dead function, let's say you would very early know that a function is dead. Would such a function be allowed to be like would the body of the function be allowed to have ill-typed stuff in there? Like, and would that still compile?
Yeah.
I see.
As long as it passes,
like lazy.
Okay. It passes the parser syntax. The parser can die on syntax. Passes parser syntax. A typing system will give you a type. Might be a really junky type, might be a terrible type, but it will give you a type. And one of the types it'll give you is this function is not reachable.
I see. I mean, I actually, I think Zig does something. I mean, obviously from a type theory perspective, not really, but like it does quite a lot of lazy semantic analysis. And I have used it in anger quite a bit. I think it's a bit frustrating because, and I guess it's a minor thing, but usually I write the function first and then I call it somewhere probably. But as I'm writing the function, I don't get type errors because it's not used anywhere. I mean,
Yeah.
actually, that's not exactly the case, but there are some cases where because of that code elimination or like if I use comp time, so it's their compile time function evaluation stuff, and it's guaranteed. So in your case, it's actually a bit worse because it's implicit, like the compiler determines if something is can be reduced to a constant, and in that case, that performs this lazy path. But in Zig, at least you have a keyword. But still, if you use the keyword to yeah.
You could have a keyword here too. There's no difficult harm, crime, whatever. Keyword just
Right.
says this function gets called by a magical mystery, nothing. You know, the compiler opaquely can't tell anymore that it can't be reached. So it can. So I'm going to optimize and type it like it can be reached. And oh, look, it's got type errors. So this is an easy, you know, it's the same solution Zig has. You throw a keyword in and it's all good.
Yeah. I just think it's a bit annoying that not all paths are tested out.
Well, that's what the keyword's for.
And it's
I mean,
it's the trade-off. You want some paths to be taken on some code, and on some code you want not be taken. So
I will say I have seen miles and miles of Java code, Java exception handling code that's never been tested, is blatantly broken should it ever be reached, but it was never reached, and it's just dead. It passes the compiler, passes Java C, passes whatever. It's obvious that were you to take that exception handler, you would die. Okay, fine. Why did you write this code? You clearly haven't tested it, because if you tested, you would have died there. So why write code you can't test? So, you know, if you're writing some function and you think you're going to hit to this piece and it's going to do something, I always start out by putting a to do there. And if I don't actually hit it, I got my invariance wrong, my thinking wrong, something wrong. If I hit it, oh, it's time to write the code now. But I don't write code that I can't like immediately test. It's just too fraught with errors.
I think this is a bit like the difference between template meta programming in C++ and like something like trait-based polymorphism, where I mean, basically, if you or something like C++ concepts. With templates, you can have errors after instantiation, so like they can happen later in this stage. But like with concepts, you push them forward. And I personally, I guess, it's just my.
you mean runtime generation of the template code?
No, not runtime. All compile time stuff. It's just that you get errors after you instantiate the template with a particular parameter, maybe.
Right. It instantiates in some cases and not in others.
Yes.
Matt's not here, so he can't tell me if he agrees, but concepts are so bad in C++.
Matt is
So
here.
annoying to write. You can write a concept and it won't give you an error, and you will have no idea you wrote it wrong because there's no warning or compiler error about it. It's the worst.
Okay,
And
let me just say,
like
I like the concept of concepts. I mean, you know, conceptually, the concept of concepts is good, but yeah, what I mean is just
in practice,
having errors
theory,
earlier.
All things work in theory, but in practice, theory doesn't work.
Matt, you're like 30 seconds too late. So what do you think about C++ concepts?
I mean, I think that making trade-offs within a large and complicated language, and that constrains your choices. For example, I think the talk was about early checking or the definition checking. So you would like to have a checking and error messages from the compiler as you're writing the definition of the function that is expressed using concepts. And you can't have early checking in C++. Sean Baxter has tried to implement this, and he ran into issues that there were basically no implementation choices that would work. There are some constraints in the like variadic templates in C++ that other languages with generics simply do not have. and all of the existing prior work simply doesn't apply. He actually has written a write-up about his implementation experience because he went pretty far actually trying to implement this. So I think this is educational.
Yeah, if you find the link,
much,
that's great.
That's a much longer answer than I thought you would say, but I was like more thinking about like writing the concepts.
Yeah.
You're muted. I don't know if you try to say something.
What do you mean?
Because I tried to write concepts the other day, and you can write a concept, get it completely wrong. There's no error warning about it, and then your
Yeah, that's
code
exactly
will...
that's exactly what I'm saying. You're when you say that you can write something that is exactly wrong and there is no error about it, you are asking for early definition checking. And what I'm saying is that early definition checking for concept is not practically implementable. So this will never be fixed, in my opinion, because it's impossible to
So it
fix.
turns into a runtime fail, which just is
No,
like C++ and runtime checks just don't go hand in hand.
It's simply going to be checked as it has always been, which is at the instantiation time. So you as the author of a function, say using a concept, will not get errors, but someone who uses your function will get errors.
Essentially, you just get that one entire screen of error messages.
It may not, I mean, that part can be fixed. That part is, quote, just engineering, unquote. You can do something like report just the first message. But it's fundamentally the problem that you, as the author of the function using the concept, will not get checking. So say you want to write a function that uses, say, random access iterator, and then you are going to use some feature that is not supported by that random access iterator, then that's still not going to be, you will still not get an error in the compiler that you have used something feature that was not supported by random access iterator. It's only the user then instantiates your function with something that turns out that does not support this feature that they are going to get the error.
It's like a library writer's nightmare. You know, I wrote a library. It used concepts. Yep. Oh my God. It works for me. This is a very classic. It works for me. No, stop.
And it's simply because with the features that you have with the concept, no one has figured out how to do early definition checking.
Wow.
I think it's a good term. Like, I guess that's what I meant. Early definition checking. Like for polymorphic code, that's my preference.
Well, it has errors when certain kinds of polymorphisms show up at it and not others. I would like to not see that in any language I design, but I can't.
And the code is only checked when it's instantiated, correct? What is what I heard?
Specialized at a particular spot, yeah. Yeah.
Yeah, so it's not as if you are going to produce wrong code. So it's maybe not as dramatic as some people say that you will get no error checking ever because you still get compile time error checking.
Yeah.
It's just from the ergonomic point of view, it would be much better if you were getting this as the author of the library instead of the user of the library.
Right. The user gets the error and the author code is fine.
So I think that when you compile something, it has to make sense. Either not, it's instantiated in the program. It has to be make sense to at least at the type level to the compiler. So if you delay that, then I don't know.
All right.
Cool stuff.
Can we put this concept to bed?
Yeah.
Hey, James, you want to do a 10-second intro?
All right. Can you hear me?
Yeah.
I don't want to introduce myself if none of you can hear me. I've had trouble with mics for some reason. Okay. I'm James. I'm on the East Coast. I'm a software developer. I used to do like C and assembly, but I'm pretty high lately. Anyway, I have a real interest in compilers, and I've been sort of picking things up over the last few months, and I'm grateful to be here.
Yeah.
Thank you.
Welcome.
Are you working on a compiler now, or language, or anything like that?
Yeah, I'm sort of doing a language mostly to learn compilers, and eventually I'd like to write something useful, at least to myself. But right now I'm mostly just playing, learning the concepts. So
I think like half the people on this channel are writing their own language, either to learn how or to do something new and exciting to themselves or something. Yeah.
Okay, next topic.
Yeah, next topic. It's time. We beat my Discord topics down. I'm looking to see if there's anything else. We had one more from Thalia, which was the renormalization done by C2 and Simple, and losing CSE opportunities. That short answer was, given an arbitrary large DAG expression of reassociative operators like multiplies and adds, there's an arbitrarily complicated algorithm you can run to go get a minimal form. And a SAT solver will find it. I don't know that there's even an n-squared solution. I think it might be exponential to find optimal. So C2 does a hack to get most of it, and he's mostly targeting the math you get out of array and structure references, and not giant arbitrary other math. And the easy, and Simple does too. And so the easy one is I just canonicalize these reassociative expressions into what I call a left spine. You have a spine, and along the spine is these social operators, add, and off the spine become other things you're adding into your giant add tree. And because you're associated that way, you can sort the right-hand sides to get all the constants together, and they can fold, get all the same values, whatever they are, bases of this or index of that, have them all fold up. So you get a bunch of optimizations that way. And then, right before code emission, C2 will do a bunch of other things to reshuffle that spine to run faster. If the spine's long, he'll flatten it to a parallel adder format so you get wide issue out of your x86. And most of them are just simple addressing math, so they just swallow into address expressions for loads and stores and things like that. But you definitely lose some opportunities that he doesn't find. I guess he also does if the expression that got computed and I want to reassociate is actually really used heavily, he'll leave it as the form and not reassociate it so that he gets all those uses. And that was your example. You had 2 uses or 1 use of something, 2 uses.
So when you're sorting, I could envision it being, so you first get it into the spine and then you want it sorted. Yeah. It could be like a insertion kind of thing. So as you build up your...
I do something much stupider. I do a local only thing that effectively does a bubble sort. And because the length of these things is typically really small, no one cares. If you go look, I only look 1 or 2 pops away. I don't scan a big thing to look for a sorted list. I have 1 or 2 hops from every node, and I rotate or not according to what you look like. That turns into a bubble sort. But like I said, they're all short. No one cares. Done. And there's no sort algorithm. Nowhere I say call sort now. No. Get to left spine also sorts, and it sorts basically with a bubble sort.
I see. Yeah.
To go write some simple code with large expressions and see, you can see the sorting in action.
Yeah, that's the code I'm working on right now. So I'm just thinking about different ways you could do it. The egraphs implementation side is just tantalizing to me because the idea of being able to express all these rewrites in a general way and just say, here is my estimates for the cost of this AST, extract the best out of this soup of saturated rewrites. That's really cool, but I also love implementing things myself. So like, I wonder how good I can get it without something fully general like that. But then writing all these peepholes with as verbosely as it is, it's just kind of like I just as an exercise, I ported my stuff to egglog, this egraphs plus datalog language, and it was so short. But
okay. I will say that the peepholes as they stand now have gone through many iteration attempts by me at least, and people around me, to better find ways to write peepholes. And the current strategy I have is, it's pretty short and sweet, and I'm happy to see a better one. But like I said, I got, it's short and sweet. Most of the peepholes have a one-line pattern match and a one-line rewrite.
Mm-hmm.
So
Yeah, as
drop
far
out.
as what I would be using egress for in this compiler, it would just be the pure expressions. So I haven't figured out how to throw control flow in there because egreffs need to be fairly structural. Like the traditional way you're matching on nodes is this thing contains this thing, and that's great for arithmetic. But once you're throwing in control nodes, then it's all messy because you could have many things depending on the same thing, but they don't own that thing, they don't contain that thing. And
This is sea of nodes. It's all just nodes.
well,
People don't care.
I
Control,
get
not
that, but
control.
like
Don't care.
I want to join the two worlds, and I'm not thinking of a good way.
Okay. You make any progress? I'd very much interested to hear, though.
Yeah, from what I've read, it seems like the most promising work in this area for joining sea of nodes with egraphs is with regionalized value state dependence graphs, RSVGDs.
Yeah.
And so I'm just learning how that works.
Yeah. I mean, I looked at PDGs many years ago, grad school level, and decided that when I went to Sun to go do hotspot, that they were just a little bit too complicated for the amount of gain you got. And so I just said, I'm going to go the simpler route. And that worked out great, although that, left some stuff on the table, but not very much.
Is simple route where, like, is that where you picked simple as the name from, or simple as in
No.
small language?
Simple was intended to be the sort of the simplest possible tutorial I could for Sea of Nodes. So the language is kind of, it has no redeeming qualities. It's just a classical Java C-ish minus stupid language. It could slowly be expanded to a better language, but the goal isn't to have a fancy language. The goal is to show compiler optimizations. So I just need enough out of it. So the simple was simple language for compiler optimizations.
Okay.
What I talked about simple a second ago, I meant out of grad school, knowing what a PDG is, I decided that the gains I got over PDG over what I was calling Sea of Nodes were not sufficient to bother. In particular, the flattening algorithm to go actually emit code out of the PDG was much more trouble than the one I got out of Sea of Nodes. So I picked my research projects carefully. Like if you're trying to implement something that's going to be real, you probably don't want to be doing a research project for it. So I picked limited counts of researchy things, and everything else was stock. And that worked out. Okay. Is that it? We all done? I'm looking for other things that came out of Discord the last couple of days. There are lots of random things. Did a big walkthrough. No one else has something. I'm willing to call it now. We've gotten an hour and 15, hour and 20 minutes in. It's all good.
I've had a question, and I sort of found an answer, but maybe there's a better answer. That there seems to be a problem with Sea of Nodes and reporting errors, because if you do the what is it? Anyway, if you deduplicate the nodes, you lose the error location information. So if there's an error later, you may be calling the wrong location. So
Okay.
I don't know if there's a solution to that or not.
Yeah, there is. There's a couple of things. So first is that most of your errors come out of the parser long before any dedupe happens. So those errors are unrelated. In the land of simple, the only errors that I'm getting after the parser are the ones where I can't figure out your null pointer situation. And I'm declaring you need to put a null pointer in. And right now, because I'm doing a compiler thing and not a tutorial and not a language quality, I don't do shit for the error messages. So they report an error, but they don't say anything about anything. You know, it's really bad. And in AA, I spent some effort on that, and that was just simply I tracked a bunch of places where things came from, and when you deduped, when you see a seed, value numbered, I would gather them up. So it's somebody who's going to proclaim an error, he would have some set of locations, all of which presumably had the same problem. And any one of them was a fine answer, but they were all simultaneously the same bad answer, or the same fine answer for the error message. So you can gather up the error points. And that, I mean, that's a quality of implementation. How do you want to see the error? The usual one, though, is that the parser says you have a syntax error, stop now.
Sure. Yeah. Thanks.
Yeah. And the other piece of that window, the counter is that AA is doing Hindley-Milner unification. And there you get error messages on the types, for which it's a lot more difficult to deduce what went wrong. And
do you, I don't remember if you talked about, do you track the type provenance, if you will, the type,
yeah.
How the type flows through the different points in order to report where it's become problematic?
I don't for the Hindley-Milner. I could. I went back and forth. I wanted to get my bugs out before I went to get my error messages better. I do track where you do a unification step that will fail, and you would report, I succeed, use an error term in the typing system. And then I'll gather up every other unification against that error, and they'll all succeed into their bucket. So the error term will unify an int and a float, and a string and a function and a struct, and all the ints and all the floats and all the strings and all the functions and all the structs will all land in their own buckets. But he'll be an error term. Okay. Somewhere along the way, I'll have gathered at least one of those points where it fails and hung on to it. And all of them are fails, but I'll have gathered, at least for the Hindley-Milner sightings, I'll gather at least one. And I'll report that one when I'm all said and done.
But it will be either the last location that the unification failed, or
it'll be the first location
or the
where
first
unification fails.
Okay.
But that has nothing to do with program order. That's the issue. So I don't track it more than the one layer deep. So the typical fail here is you have, for instance, called a function with fewer args than necessary. So it's curried silently under the hood. So instead of getting the function result, you have a function that's missing an argument before it can run and give you a result. You pass several of these along through a bunch of nested function calls, and eventually you come up to the point where you use the expected result, and instead you have a function missing an argument. And now, instead of having an int or a bool, you have a function which, were it given a missing argument, would give you a bool. And you're like, where the hell did this come from? And so I give you the point right there. Hey, this is a bug. Okay, fine. But now backtrack, that's a bitch. I don't track all those. So when I was debugging these kinds of things, writing this kind of code in the past, the easy answer was I had been doing type inference for a long ways. I needed to back up and write a type annotation. And then I would fail at the annotation, which was an earlier point in the typing process. And I would get closer to where the real bug was.
That's the common debugging in the Hindley-Milner type system. Just put the types and see how far it gets.
Yeah, keep adding annotations and you narrow down where the bug is. And then the annotations are supposed to be correct anyhow, so you just leave them in. And they're good documentation, whatever. You got too aggressive with inference, you needed annotations to find it.
Yes.
So I don't have a really good answer here. I could, at every unification step, track where both sides came from, and that would be a big pile of stuff. And then if it's an error, is it still the right set of things to tell you how you got here, that you have an error? You know, here I say function taking an X, returning a bool, and you have an if test once a bool. So you got a function, not a bool. Okay. So a unified Boolean function fail. Where did the bool come from? Well, it came from the if, and I'm done. I think that's a root cause. And where did the function come from? Why are you passing this argument? And it unified here, and it unified there, and it unified to this, and blah 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 blah. And you walk long way back. At no point did it ever come up to, I took an original function, I added 3 out of the 4 args, and I left with a function back instead of a bool, right? And I'm not sure how to arrow that right.
Backtracking would be expensive. They track.
And then right, and then the debug info for the error message starts to gather on you. It gets big.
Yeah.
I don't know. So I'm not trying to code in Anger on AA yet. I have coded in Anger in Elm and by proxy Haskell, and you know, suck, and add annotations and go again, 3 or 4 annotations adding, and suddenly I'm like, oh wait, this is not supposed to be a fucking function. Everything's a function, so they're all functions. Like, oh, it's not supposed to be this kind of function, that kind of function missing an arg. Okay, wait. Oh, here I'm supposed to pass the person in as well as the this and the that and the da 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 da.
We at this point we just can guess the AA program has to become large, and that will highlight.
That's my current theory. It's large. I'm not going to solve it now. Add your annotations when I get to it. I've had to do all kinds of projects, right? Just back from Burning Man, all kind of other projects going on. So I haven't done any AA in a while. It's really hurting me, and I want to get back to it. But this week I'm doing Simple and Ecstasy, and next week I'm going to be doing Darrick's work, and AA's on the back burner again. Fine.
Life happens.
Yeah, and life happens, exactly.
Okay, cool. Anybody had some topic?
That's all good.
Yeah.
All right.
We gathered to an hour and a half, so.
Yeah, we're good. All right, Darrick, you just lit up your video. You going to say something? You are.
Yeah, no, well, I was thinking, I have some stuff, but nothing very exciting. So I think maybe I'll save you guys the trouble.
All right, is this an update on your project?
Yeah, I mean, the main thing is that I'm running end to end now, and I started running on our house simulator, but it's just annoying. So on Tuesday I decided, you know what, I can build a quick interpreter and just run, you know, like do what I need so that I can actually test in process and not have to go off to some external machine that's sitting in a server somewhere else and run tests.
Optimize your workflow.
I did that. And so now I've got this nice simulator that gives me lots of information about what it's doing that's relevant to me. And yeah, now that has already sped up my testing cycle a lot. So happy with it. And I found this very nice, very simple Risc-V interpreter that someone open source. It was written in C++, but it was so nicely and simply written, or C maybe, so nicely and simply written that I was able to port it over to Java in about a half an hour.
Wow.
And like basically just almost copy and paste and like make a couple syntax edits, and it was, yeah. And so it's like one of those header only projects that sometimes people do. Let me find the name of it.
Yeah. Oh no, but did you then go and add the processing element side of things?
Yeah. So that the porting the Risc took, you know, maybe a couple of hours. Adding the processing element stuff in the same vein took another day and a half, and so now it's all there.
Oh, so, interesting.
Yeah. So so it's actually called Mini RV32 IMA, which is not much of a name, but it's
throw the link in the doc.
Yeah.
So give people credit, and they can all find it offline here as well.
Yeah. It's by someone whose GitHub name is Nolor. I'll throw it in the chat here first, and then I'll find the doc.
Okay.
So it's there.
Yeah, we'll just throw that link in the doc.
Yeah. Okay.
Yeah, mini. Yeah. Okay. Right. And it does the 16. Aren't you guys on the 16?
It does pretty much the exact instruction set that I wanted.
Okay.
So yeah. Oh yeah. Someone already threw it in the doc. So That is like just a very nice little Risc machine. There were a lot of other ones. They were way more complex.
Mm-hmm.
And this one's just like
Perfect.
one big
Good.
case statement. It actually looks a lot like the Verilog that our Verilog guy used to implement our Risc core, to be honest. So
Excellent. Well, I look forward to looking at it.
It'll be next week.
Yeah.
Well, it's coming up. It'll be a couple days.
I got
Out
more
of
things to do.
curiosity, are you doing compressed instructions in Risc-V?
yeah, we do support the compressed instructions, but for now I'm just ignoring them.
Yeah, so what are your thoughts on that?
They are rarely valuable because they require so much extra setup as far as I can see. So you know, you have compressed instruction, but you almost always need more instructions to set up your compressed instruction. So I suspect that they might be useful inside a loop where lots of the setup is loop invariant, but I don't know when that happens. And then they can cause alignment issues, at least in our hardware, which can cause you occasional pipeline stalls.
How about you just throw some knobs in, but that's a pipeline.
Yeah, you need to throw a knob in. So you need to be good enough at knowing when you need to throw a knob in, which I don't think is that hard, but.
I did titanium back in the day on a
Maybe-
fucking
So maybe more trouble than it's worth, in a sense.
Intel BLIW titanium for hotspot. I got throwing knobs in down to a fine art.
Yeah.
So,
Yeah.
so what does your hardware do? Was it like accelerator stuff or?
Yeah, it's
or-
an AI accelerator for inference.
Oh, for inference, I see. Also,
Yeah.
something like these 10 torrent cards. Is
Kind
that
of like
something
that,
similar?
Yeah, Tens torrent is so I mean Tens torrent seems to be more focused on building Risc cores for like high-end CPU applications now. And I'm not sure how much focus they have on their accelerator side anymore, but yeah, they have those accelerators they built when they were a younger company. They're pretty cool.
Wait, so does that mean? Oh, sorry.
Yeah, no, yeah, I don't know. What were you gonna say?
I was wondering, like, so does that mean that the actual kernels that you execute on your hardware are written in Risc-V? So those are the payloads?
Yeah, there's this hardware hierarchy. So we have a Risc-V, but its main job is generating instructions for a little machine that's running beside it, and that little machine is like a SIMD engine, and it runs asynchronously to the Risc core. So you can sort of queue up lots of work. You can set up loops to run in that.
Okay, so the Risc-V chip is not in the data path, really. Like,
No, that's right.
Yeah.
It can be. It can pull data in if you need to do something weird, but generally you don't want to do that because it's way slower than the SIMD engine that it's trying to drive.
Yeah, if I found it interesting. So I mean, most so I'm more familiar with like network cards, so and accelerators there, like SmartNICs, because they also have like an off-path like management kind of core, like or CPU, like something like a 16 core ARM sometimes, or less core ARMs or whatever. And then it has its own like DDR, and then it speaks to some data path accelerator, which is either like some kind of weird SIMD stuff, something proprietary. It can be also GPU stuff. But what I find interesting is that actually like one SmartNIC, I don't remember which one, but that one actually tries putting Risc-V in the data path. So basically it's a 128 core Risc-V chip that actually executes like packet processing stuff instead of typical FPGA things or like more complicated things. Just putting Risc-V in there. I find that very interesting. I wonder if that actually will be sustainable or a good idea in the future. But yeah, I think the design space for this.
Tight little programs, I would think. Otherwise, you're gonna slow down the data path, or there's presumably some sort of merge step where if one piece is taking too long, everything else backs up.
Right. Yeah. Usually these yeah, packet processing rules are like, quite constrained, very short. So yeah, I think you're right.
Yeah, but it might work because like the data flow is relatively low. I mean, even though like a network card, it's like 100, what is it, 100 gigabit or at the most. So it seems like a lot, but if you've got a lot of processing you can put on one chip. So that 100 gigabits isn't really that much data to deal with if you've got a bunch of cores. But it's neural nets, it's worse because you've got potentially similarly high rate data coming in, but you've got huge workloads that's going on that data.
Right. Yeah, I mean nowadays it's 400 or 800 gigs, but like I think it still applies.
Yeah.
Oh, cool. Thanks.
Yeah.
All right. Anything else? All right, I'm gonna call it. It's a good coffee club. Hope to see people next week.
Bye.
Thanks.
Bye.
Bye.
Bye.